Hello class, this is a follow-up lesson to relative atomic mass. We're just about to get into the real heart of the course, and this is a real pivotal lesson because it opens the door to our understanding of how to deal with chemical reactions on a scale that we experience in the lab. We're working with gram masses and we're measuring out samples that have um, huge numbers of molecules, ions, atoms, etc. So how do we deal with chemistry on this scale? Well, we need a unit. We need a quantity that allows us to work with the masses that we already are familiar with, relative atomic masses. Here's a periodic table of the elements. And of course, we have the element symbol. We have this atomic number of protons, but we also have this relative atomic mass, which is in atomic mass units. Now, an atomic mass unit, as you remember, is an extremely small value. Now, previously, we looked at atomic structure and we summarized the different particles in an atom. And we know their locations and we know their relative charge and we also know the relative mass. But scientists, chemists also know the actual mass of proton, neutron, electron. And when we assign relative mass of one atomic mass unit for a proton and one atomic mass unit for a neutron, we're essentially putting the atomic mass unit in the range of 10 to the negative 24 of a gram as extremely, extremely small. So we do have an equivalence that would allow us to go between atomic mass units and grams. However, when we do chemistry in the lab, we don't mass out chemicals on the scale of 10 to the negative 24 grams. We might mass out chemicals on the scale of, 1 gram, 10 grams, maybe 100 grams, a half a gram maybe, but definitely something that would be in that range of 0 to 1, 1 to 10, maybe 10 to 100. So we need to bring up our scale from atomic mass units up into grams, and this is why we need the mole. So just recall, stoichiometry is the study of quantitative relationships. In chemical reactions, we have masses, reactants and products are being massed. We need exact masses, and we might be working with concentrations of solutions, or maybe a concentration of a gas, a pressure of a gas. We need to know these exact masses. On a lab scale, we need to work on gram scale typically, or possibly even larger than that. So chemists realized this problem that atomic mass units wouldn't be sufficient to allow us to do very much in the lab. So chemists really invented this idea of the mole. It's scientifically based, of course, and the determination of this number that you see before you has been verified in lots of different ways. The mole is really a number of particles. A mole, denoted by Avogadro's number, capital N sub little a, by experimental determination, is approximately 6.022 times 10 to the 23 particles. It's an extremely large amount. It obviously has a lot of zeros there, and it's difficult to even pronounce that number. It's so large. This is the number of particles if we're trying to figure out why. Well, here's the what. A mole. What is a mole? Well, a mole of magnesium atoms is Avogadro's number of atoms. We could be talking about a mole of molecules, where we have two hydrogen atoms sandwiched together as a diatomic molecule. That's also 6.022 times 10 to the 23 molecules. A mole of calcium oxide units would be that many formula units. A mole is a little bit like a dozen. When someone says, I would like a dozen eggs, well, they know you mean 12. If you ask for a dozen donuts, they know you mean 12. In chemistry, dozens are insufficient. 12 atoms or 12 molecules would still be on that very, very small scale of mass, somewhere in the neighborhood of 10 to the negative 24, 10 to the negative 23 units. That's literally a trillionth of a gram is way, way too small for us to work with. So the rationale for the use of this number of particles is as follows. For any given element, the mass of this number of particles, we would be probably referring to atoms, exactly equals the relative atomic mass, except in grams instead of atomic mass units. Okay, so let's go back to the periodic table and I'll explain what this means. Let's choose, for example, a really obscure element. Maybe we've never worked with ruthenium before. Ruthenium. One atom of ruthenium has a relative atomic mass, which is of course an average of all of its isotopes, but it's 101.07 atomic mass units. Now, if we scale up from one atom to Avogadro's number of atoms of this element Ru, we would find that that number of particles is necessary to get our value from 101.07 atomic mass units into 101.07 grams. There had to be a magic number that would bring all of those relative atomic masses from that very small unit, the atomic mass unit, up to grams. And that's what the number is. All right, and the wonderful thing about this concept of the mole is it allows us to do that across the entire table of the elements. We choose any element, given its atomic mass in U units, atomic mass units. We can go directly from that to grams if we consider Avogadro's number of particles, that being 6.022 times 10 to the 23. And this is a huge number of particles. That's how many it took. A dozen would not be sufficient. A trillion would not be sufficient. That's how many particles it takes to keep that number the same, which is of course very convenient. Now we're just changing our unit, and that's all we really need to consider when we're calculating the mass of a mole. Now is new unit, same number. So let's have a look just how exactly big this value is. Well, in science we talk about orders of numbers, and when we say the order of the number, we're referring to the power of 10. We've been working with this a little bit in significant digits with scientific notation, and it's been a source of frustration, and there's probably some success we're having at that, and we'll keep getting better at that. But Avogadro's number is on this order of 10 to the 23. So here's some ways we can think of this number. If each of these boxes contained 100 particles, that's pretty small. We would need a billion trillion of those boxes to make up to Avogadro's number, and that's really only getting to the order of the value. It's not even considering the fact that it's 6 times bigger than that. If we had all the way down to the end, if there were a trillion particles, which is a huge number of particles in this box, if there were a trillion particles in that box, we would still need 100 billion boxes. That's huge. Okay, we need 100 billion boxes to actually make up just to the order of Avogadro's number. And then we would need 6 times more than that to actually match Avogadro's number. So it's a lot of boxes and a lot of particles. We don't really want to do chemistry by counting atoms, molecules, ions, etc. We just need to know how many we need to work with so that we can actually start to calculate the mass of reactants and products on a scale that matches what we do in the chemistry lab. All right, so we're starting to get an idea of what this mole is all about. A mole is like a dozen. It's a number of particles. Now what we can do is we can talk about molar mass, okay? So Avogadro's number is the mole, that many particles. We can later calculate the number of particles that a certain sample represents. If we have exactly 1 mole, we have that many particles. If we have 2 moles, we have double that. If we have a half a mole, we have half that many particles. But let's just focus on just exactly what we can do directly with this this concept of a mole? The most obvious connection is to describe the molar mass. So this is given the symbol capital M. It's in grams per mole. Okay, a little bit like, say, pounds per dozen, if we were talking about maybe a dozen apples, or say a dozen donuts or whatever it would be. We could come up with a similar unit, but our unit here is grams per mole. So we're saying 1 mole of an element or a compound has a mass of this value, molar mass. As long as we understand it represents that many particles, we go to the periodic table and we can do some calculations directly from our relative atomic masses. So here's the steps. It's pretty simple. We need to know the chemical formula. Once we know the chemical formula, we just identify the number of atoms or possibly ions of each element. We add up the total of all of the relative atomic masses and we report the answer in grams per mole. So let's look at a couple of examples here just to start out. Let's determine the molar mass of these two compounds. Now, chlorine is diatomic, is molecular. It's covalent bonding, but we're not really interested in that right now. We're just trying to calculate the molar mass. Okay, but remember, distinction here is that chlorine does actually exist as an individual molecule. Okay, so when we're considering here 1 mole of these molecules, so a mole of chlorine gas would be capital M, would use a subscript for the chemical formula, and we would say that, well, there are 2 atoms of chlorine, and each atom of chlorine has a relative atomic mass of 35.453. Therefore, if we were considering a mole of chlorine molecules, we would have 2 moles of chlorine atoms. Okay, now let me make that distinction here. A mole of chlorine molecules would has 2 moles of chlorine atoms. Okay, so we're calculating the molar mass for Cl2, but we have to recognize that Cl2 is diatomic. And so what we're really doing is we're calculating on the basis that a mole of chlorine atoms is not 35.453 atomic mass units, it's 35.453 grams in its mass, and we have 2 of them. Okay, and so that would give us approximately 70.906. We can calculate the exact value if we want. Okay, and we do 70.906. Notice carrying through 5 significant digits because 2 is counted value. We're talking about 2 exact moles of chlorine atoms. There's no uncertainty in that, so we're going to carry through 5 significant digits in our answer. Let's look at the molar mass of an ionic compound. Now here, there's no such thing as a molecule of calcium hydroxide, but we do have a formula unit, which means that on a very small scale, we have 1 calcium 2 plus ion for every 2 hydroxide ions. Okay, so when we look at the molar mass of calcium hydroxide, we're looking at really the molar mass of a calcium atom and the molar mass of 2 or twice the molar mass of an oxygen atom. And we're looking at twice the molar mass of a hydrogen atom. Okay, and that's based on this step right here. We're counting the number of atoms of each element, or in this case, well, they exist as ions in the compound, and there's a little bit of a comment I need to make here. Calcium ion and a calcium atom don't have exactly the same mass because the ion has lost, what? 2 electrons. But where have those 2 electrons gone? Well, they've been transferred onto the oxygen and the hydrogen polyatomic group. So are they still included in the mass? Yes, they're still there. So the easiest way to approach the molar mass for an ionic compound is just to, again, add up the total of the relative atomic masses. We don't need to make any adjustment for the difference in mass for having lost two electrons because, of course, the hydroxide ions, and there are two of them, have gained those two electrons, so they're still there. So we would go to our periodic table, we look at the relative atomic masses for calcium, oxygen, and hydrogen. Pretty soon you get pretty good at memorizing some of these numbers. The ones that use more commonly, like carbon, nitrogen, oxygen, hydrogen, you'll start to remember those. Calcium is 40.078. And twice 15.9994 for oxygen, and twice hydrogen at 1.00794. It's a little bit more precision there. 1.00794. Okay, so that finishes it off. And that's keeping in mind that a mole of calcium hydroxide units would have 1 mole of calcium atoms, 2 moles of oxygen atoms, and 2 moles of hydrogen atoms. And there's a little bit of a obviously a misrepresentation there because we're really dealing with ions, but as I explained before, excluding electron transfer, that's how many particles of each element we have. So we can add those all up and we can get our molar mass for that ionic compound. And our final answer there in grams per mole is 74.093 grams for 1 mole of calcium hydroxide formula units. Notice how I've rounded my answer. If you're remembering the rules for significant digits, here we are adding, and we're going to go with, you guessed it, the least number of decimal places. We have 4 decimal places for the molar mass of oxygen, 5 for hydrogen, and only 3 for calcium. So we're limited by that value. 3 decimal places would be how we have to report our answer. All right, is it starting to sink in yet? Well, let's look at a couple more examples. And eventually this just becomes a process, and it's easy to calculate the molar mass once you know how. It's good to understand what we're doing here, and we're going from the atomic scale up to the molar scale, and we're just changing the unit on the value. So we look at sucrose. It's a fairly large molecule. It has 45 atoms, and of those 45, 12 are carbon, 22 are hydrogen, and 11 are oxygen. Now, if we were to consider 1 mole of sucrose has a lot of atoms, but 1 mole of sucrose has 12 moles of carbon, 22 moles of hydrogen, and 11 moles of oxygen. Now, I don't want to say that's obvious because sometimes students, when they're first introduced to the mole concept, this is what they struggle with the most, is that we're talking about 1 mole and now suddenly you're saying there's 12. Okay, how does that work? Well, it depends on what we're referring to. If our unit is the molecule, I could say I have 2 molecules. I could say I have 12 molecules, 100. I could say I have Avogadro's number of molecules. As soon as we go up to Avogadro's number of molecules, now we're on the mole scale. All right? And the scale of moles now is considering that number of particles. Well, because the molecule is made up of 12 atoms, 22 and 11 respectively, we will have that many multiples of Avogadro's number of each of the elements. All right, and once we get our minds around that idea, that just works. The molar mass of the compound C12H22O11 just simply becomes, again, probably the easiest way to introduce it at first is 12 times the molar mass of carbon, 22 times the molar mass of hydrogen, and 11 times the molar mass of oxygen. And then the numbers come from the periodic table, and the calculation is just adding values together. So there's my answer. If we had Avogadro's number of sucrose molecules, it would only take about a pound of sugar, 342 grams. So not much, which makes us realize how many molecules we're working with whenever we dispense relatively small amounts of chemicals in the lab setting. Now, just a comment on significant figures. in the final calculation, we're going to keep 3 decimal places. We're adding numbers here. Okay, now it might look like we're multiplying, and um, you might be thinking, well, I'm gonna multiply those products together, and I know that 12, 22, and 11 are defined and counted whole values, so they have infinite certainty. So I'll keep 5 significant digits for the 12.011, and I'll keep 6 for the product here, and I'll keep 6 for the product there. And then when I'm adding them together, I'll just look at decimal places afterwards. The problem with that is when we multiply these values, they get bigger, of course, and we start to, in some cases, lose decimal places if we try to hold on to 5 significant digits or 6 or 6. And the best way to explain why we shouldn't do that is because 12 times 12.011 would really just be a whole bunch of 12.011s all added together. Okay, and clearly if we were to add them all separately, we would just use the rule for addition, which would be fewest number of decimal places, which is 3. If we were to add 22 1.00794s, again, we have 22 numbers that have 5 decimal places. That's more than the value for carbon, so we're limited by 3. We add 11 more numbers which have 4 decimal places. Again, that exceeds the limit of our precision. So we're going to fall back on reporting to 3 decimal places because of the lower precision for carbon. So the primary operation involved in calculating molar mass is addition. And all we need to do is look at the relative atomic mass that has the fewest number of decimal places, and we'll report that as our final answer, which would be 342.300 grams per mole. So one more example, and that will close off here your introduction to the mole. All right, octane. So for the 4C students, you'd be familiar with the hydrocarbons, the alkane group. They fit that pattern, N carbon atoms and 2N plus 2 hydrogen atoms. So there's a connection for that group. So octane is 8 carbon atoms, 18 hydrogen atoms. So if we were to consider not a molecule of octane, but a mole, Avogadro's number would contain 8 moles of carbon, 18 moles of hydrogen, and the molar mass, capital M, for the molecule would simply be the sum of those two products. Again, keeping in mind we're looking at decimal places here. This is an addition operation for molar mass. So we have approximately equal to 114.231 grams per mole. And that's not that much. You know, if you were to dispense 114 grams of gasoline into your engine, you know, you're looking at less than a cup of gasoline there. And that cup of gasoline, or that less than cup of gasoline, has Avogadro's number of molecules of this compound. So the work in class that we can start to practice with, here's some questions from your textbook as well. And I've just added a part number 13 there. It's important to be able to understand the difference between moles of a molecule and moles of atoms in that molecule. You've seen some examples here. This worksheet here is another one that will kind of lead into our next section where we kind of formally define some relationships between moles, particles, and mass. So for now, these are just for us to consider how would you answer these questions, and perhaps you have an opportunity to, at this point, you know, pursue these types of questions. If you're still struggling a little bit, then I would go back and look at some of the examples in the textbook. And if you want to keep going with this video, I'll just work through these last 3 examples, and then that'll close us off. So at this point, number 4, 5, and 12, I believe these are being pulled from the textbook from section 4.3. How many molecules are there in 3 moles of carbon dioxide? So carbon dioxide is a triatomic molecule. If we had 3 moles of those molecules, we have really 3 multiples of Avogadro's number. All right. That means that taking this unit and scaling it up to a mole, we now have that many which means that we would have 3.00 times 6.022 times 10 to the 23. Avogadro's number actually has units. This number would have units of moles, and the second number would have units of particles per mole, because that's what it is. That's 1 mole has that many particles on Avogadro's number of, on that scale. So we're simply looking at the product involved there, and it's got a base 10 exponent. So we're going to just take out our calculators, and really all we need to evaluate here is the initial product. But what's going to happen here when you multiply 3 by 16, you're going to exceed the next power of 10, and so your order of magnitude, which is how big your number is, or how small the number is going to increase into the range of 10 to the exponent 24. So if you enter this in your calculator, you just simply put in 3.00, multiply it by 6.022, and you do have a button on your calculator that allows you to put in scientific notation. If you haven't seen that before, it's probably an EXP button or possibly a 10 to the X button. So simply follow up the 6.022 with that order of magnitude of 23 and complete your product, and you're going to get a new answer, which would be 1.81 approximately times 10 to the 24. And that, of course, would be in units of particles, because sort of our unit cancellation here works for us. That many moles, that many particles per mole will have that many particles. In this case, the particles we're talking about are molecules. So we have molecules of CO2. Okay. Now, let's say we look at the atomic scale. So if we have, this one's a little bit easier because actually this is an atomic element. So argon is monoatomic, and if we had half a mole of argon, well, that's going to be a half multiplied by Avogadro's number of argon atoms. And so our amount here would be .500 times 6.022 times 10 to the exponent 23. And again, this is moles, and this is, if we want to put a specific type of particle, we put atoms per mole. Okay, because we know we're dealing with atoms here, so before we could have put molecules. Whatever a particle is, when we consider a mole of them, it fits in all cases. So half of 6 would be 3, and it's a little bit more, 3.011 times 10 to the 23. Of course, significant digits applying here. We would have to round our answer to 3.011. Sometimes what you can do is you can underline the significant digit that you're actually going to use in a further calculation if you were. Otherwise, I would just round that to 3.01 times 10 to the 23 atoms. And the last one, if the molar mass of a substance is 67.2 grams per mole, what is the mass of 8 moles of the substance? So this is extending a little bit more into what we're going to look at in section 4.4. But let's consider this. We don't know what the substance is. 67.2 grams in 1 mole. There might be different ways of getting that. Let's look at a periodic table and find what element could be closest to that. So 67, maybe somewhere between gallium and germanium. So it's not either of those, so it can't be an atom. So it would have to be a molecule. Maybe it's an elemental molecule. Maybe it's two, well, even sulfur and chlorine double don't give us 67, so it's not diatomic chlorine. So whatever it is, that's not really important here. We don't even need to know the identity of it. What we're dealing with here is just simple relationship that 1 mole, and maybe it's important that at this point we emphasize that it's grams per 1 mole. Just like when we travel down the road, we drive at, let's say, 98 kilometers in 1 hour. Or if we work somewhere at a job, we might earn, say, $11 for every 1 hour. Okay, so it's a unit ratio. So 67.2 grams in 1 mole, simple scale factor here. If we had 8 moles of the substance, then we're going to have 8 moles, and for every mole, we mass accumulates at 67.2 grams for every 1 mole. No formula needed here, just a simple ratio, looking at units and how the units interact. A lot like calculating how far you've driven in a certain amount of time, or how much money you've made in a certain amount of time. And this is going to introduce a formula in our next section. But for now, numerically, we can see how these numbers would interact. 67.2 times 8 would give us 537.6, which is the mathematical answer on a calculator. Anything missing here? Sure there is. 2 significant digits is our limiting value for the number of moles. The trailing 0 is significant because it follows the decimal place. So in this case, we would have to round that to the nearest tenth, and in this case that would be 540. Now what we don't want to do is we don't want to say 540, because 540 could have, if we put a decimal place there and more information after, could have more than 2 significant digits. 540 works, which in this case is okay. It has 2 significant digits. The alternative would be to say, well, let's just be doubly sure here, or doubly safe, and just go into scientific notation. And when we do that, again, we separate out our answer into, again, those 2 portions that I talked about in class, the size of the number and the digits of information. And so 5.4 times 10 to the exponent 2 grams would be another way of representing that. And of course, that's been rounded, so it's approximately equal to, meaning those 8 moles of substance would have a mass of approximately 540 grams. All right, we'll see you in class, and look forward to hearing what kind of questions you have about this topic.